Hello everyone and welcome to section 7.1, Eigenvalues and Eigenvectors. Okay, so the way we want to look at eigenvalues and eigenvectors is first think of A as a multidimensional function. Okay, that means you take a vector x, you apply it to A, and you output A times x, where as long as A is a square matrix, then you're taking a vector from Rn to Rn. Now, often such functions have special directions where the input vector is parallel to the output vector. That's what we're going to focus on today. So let's take the matrix 1, 6, 2, negative 3, and let's compute A times V. Okay, first off, let the vector V be 3, 1. So you're taking 1, 6, 2, negative 3, and multiplying by 3 times 1. What do you get? Okay, well, you get 1 times 3, that's 3, and 6 times 1, that's 1. And so add them together, it's 9. Here you get 2 times 3 is 6. Negative 3 and 1 is minus 3. 6 and minus 3 is 3. So the question that we are answering right now, is there anything that I can multiply 3, 1 by and get 9, 3? Okay, if so, what is that value? Okay, and obviously it's clear the answer here is 3. Okay, so lambda equals 3 and the vector 3, 1 are eigenvalues. So this is an eigenvalue and this is an eigenvector. Okay, because the input vector 3, 1 is parallel to the output vector. In other words, there's a scalar that I can multiply the input vector by and get the output vector. That's really the process that we're looking at right now. What happens if I make V 1, 2? Okay, do the same process. 1, 6, 2, negative 3, multiply it by 1, 2. You get 1 times 1 and 6 times 2, so that's 12 and 1, that's 13. And that's 2, and that's negative 6, so 2 minus 6 is negative 4. So the question is there a value I can multiply 1, 2 by and get 13, negative 4? Okay, and no such lambda exists. All right, so 1, 2 is not an eigenvector for the matrix A. Last one, look at 1, 6 and 2, negative 3, and multiply 1, negative 1. Okay, and let's see what we get. We get 1 minus 6, that looks like it's minus 5, and we get 2 minus the negative 3, so 2 plus 3 is 5. And say, can you multiply the input vector, 1, negative 1, and get the output vector? Can you multiply the input vector by a scalar and get the output vector? Sure. How about lambda equals negative 5? Okay, so lambda equals negative 5 is an eigenvalue that corresponds to the eigenvector 1, negative 1. Eigenvalue and eigenvector. So for this 2 by 2 matrix A, we have found two eigenvalues and corresponding eigenvectors. Okay, are there more, or is this it? Well, that's going to be determined in the examples to come. Okay, so here's your definition for a square matrix. If there's a vector v that's not the zero vector, and scalar lambda such that AV is lambda v, then V is an eigenvector of A, and lambda is the corresponding eigenvalue. All right. So, next question. Given an eigenvector to A, it's easy to find the corresponding eigenvalue. So if I tell you that 3, 1 is an eigenvector, okay, you multiply the 3, 1 by the vector A, you see what the output is, and you find the scalar that you multiply the input by to get the output. Now, what happens if I give you an eigenvalue? Can you find the non-zero eigenvector associated with it? Let's take a look. So I give you the matrix 1, 2, negative 1, 4. And I tell you, oops, sorry, not equals. And I tell you that there's some vector out there that when you multiply it by the matrix A, you get it to be 3 times the vector that you plugged into it. Okay? So what is the vector that I plugged into it? We don't know. So we will give it components x and y. And we will solve. So 1 times x and minus 1 times y gives me x minus y. And that's going to be equal to, what, 3x? And 2x plus 4y is going to be equal to 3y. Okay, and we need to find the x and y that makes this true. So if I take this bit of information and I can add y to both sides here and subtract 3x, and we get y equals negative 2x. Okay, what about here? If, well, I'm going to get the same bit of information if I subtract 3y from both sides and subtract over the 2x, I'll get y equals negative 2x. Okay, so what do we have here? Okay, we have the first component is x, and the second component, which is y, is negative 2x. So that means all vectors of this form, where once the first component is established, the second component is negative 2 times the first, are eigenvectors that correspond to y equals 3. Okay, so in other words, it's any vector that is a scalar multiple of 1, negative 2. So let's look at that in action. Okay, let's take a quick example. Okay, let's look at the vector 1, negative 2. And let's do the same thing, 2, negative 1, 4. And let's multiply by 10, negative 20. Okay, so this is just 10 times the vector 1, negative 2. My claim is that both of these will be eigenvectors that correspond to lambda equals 3. So 1 times 1 is 1, minus 2, or minus 1 times negative 2, so that's plus 2. 1 plus 2 is going to be 3. And this is going to be 2 minus 8. Is that right? 2 minus 8 is negative 6. And you can see right here that 1, negative 2 times 3, that's our corresponding eigenvalue, is equal to 3, negative 6. There you go. So it is true that 1, 2, negative 1, 4 times the vector 1, negative 2 is equal to 3 times the vector 1, negative 2. Okay, let's see if the same thing holds here. So this is 10 minus a negative 20, so that's 30. And that's 20 minus 80, So 20 minus 80 is negative 60. And is this equal to 3 times 10 negative 20? So 3 times 10 is 30, 3 times negative 20 is negative 60. That's true. All right. So any vector of the form, any vector that's a scalar multiple of 1, negative 2, will be an eigenvector that corresponds to lambda equals 3. All right. So given an n by n matrix, A, how do you find the corresponding eigenvalues and eigenvectors? Okay. Well, again, you're looking for all the vectors v that when multiplied by A is equal to the scalar lambda times v. So if I were to subtract off lambda v from both sides, you'd have AV minus lambda v is 0. Okay. Now, because lambda is a scalar and v is a vector and A is a matrix, what I'm going to do is I'm going to take lambda v and I'm going to multiply lambda v times lambda I, where I is the n by n identity matrix. Okay. Now, this is a difference of two vectors, okay, AV and lambda IV. But this vector here is being multiplied by an n by n matrix. This vector here, this vector here is being multiplied by an n by n matrix. So when I factor out a v from behind, I'm taking the difference of two n by n matrices, and that difference makes sense. I couldn't do it if I wasn't multiplying the second term by the identity matrix. All right. So now this equation at the bottom makes sense. A minus lambda I times v is equal to the 0 vector. Now you're told that v is not the 0 vector. Okay, so this matrix times a non-zero vector is 0. Okay, that is only true when A minus lambda I is not invertible. And if it's not invertible, then the determinant of A minus lambda I is 0. Okay, the determinant of A minus lambda I is referred to as a polynomial, it's a polynomial P of lambda. It's called the characteristic polynomial. Okay, and we will compute the characteristic polynomial to find whether or not a matrix has an eigenvector and corresponding eigenvalue. Let's take a look. So now you're not told what the eigenvalue is, and you're not told what the eigenvector is, and you can't use one to find the other. So how you do it, you take the determinant, so this is letter A, take the determinant of the matrix A minus lambda I. So what is the matrix A minus lambda I? Well, it's 0, 1, negative 2, negative 3, minus lambda times the identity matrix. That's lambda, 0, 0, lambda. I'm multiplying lambda by the off diagonal, but 0 times lambda is 0 and 0 times lambda is 0. This identity matrix has 1s along the diagonal, so when I multiply it by lambda, I get lambdas on the diagonal. And when I take the difference of this, I get 0 minus lambda, that's negative lambda. 1 minus 0, that's 1. Negative 2 minus 0, and minus 3 minus lambda. Minus 3 minus lambda. Okay, now, really what's going on here, that's a 0 right there, 0 minus lambda, is everything that's in the off diagonal will be left untouched. So leave it as it appears. Everything that's on the diagonal is going to be subtracted by lambda. So take this value, subtract it by lambda, you get that. Take this value, subtract it by lambda, you get that. Okay, and this is A minus lambda I. All right, so we're going to take the determinant of the matrix, what? Minus lambda, 1, minus 2, minus 3, minus lambda. And we want that determinant to be equal to 0. Okay, to find, so we're going to find the solutions or the roots to the characteristic polynomial. What does that look like? Minus lambda minus 3 minus lambda. So that's the determinant of a 2 by 2 is the product of the diagonal minus the product of the off diagonal. So it's minus a negative 2. The product here minus the product there. And that's equal to 0. So we get minus negative 3. So that's plus 3 lambda. Negative lambda, that's plus lambda squared. Plus 2 is equal to 0. So lambda squared plus 3 lambda plus 2 is equal to 0. So lambda lambda minus 2 times lambda minus 1 is equal to 0. So lambda equals 2 and lambda equals 1. Our potential, okay, we don't know that their eigenvalues yet. To confirm it, we have to find the corresponding eigenvector. Okay, so what is that? How do you find the corresponding eigenvector? Okay, make sure I'm answering the question. Find all eigenvalues and eigenvectors. Perfect. Okay. So let lambda equal 2. Okay. Now, the next step in finding this eigenvector is to replace lambda with your potential eigenvalue in the A minus lambda I matrix. So you get minus 2, 1, minus 2, and let's see, if lambda is 2, minus 3, minus 2, that's minus 5. Okay. And something doesn't look right. Oh, sorry about that. I knew I came into a problem. This is lambda plus 2 and lambda plus 1. Okay, so that makes this minus 2 and minus 1. I know y'all are yelling at the video, saying, come on, dummy, get it right. All right, so now let's substitute. Lambda equals negative 2. What does that look like? A negative 2 is positive 2. That's 1. That's a negative 2. And minus 3 minus a negative 2 is minus 3 plus 2. That's negative 1. Okay, so at this point, we row reduce. Okay, these are all steps that we could have used the technique on the first page. Where's the first page? We could have done the technique on the first page where if I give you an eigen value, then find the corresponding eigenvector, okay? But I'm giving you a more streamlined version of that. And row reduce. So how do we row reduce this? Okay, well, add row 2, 1, and 2 together and make that our new row 2. Okay? So that row reduces to 2, 1, 0, 0, which is really 1, 1/2, 0, 0. And find the null space of this matrix. Okay, so what's the null space here? We get, there's a pivot there, there's not a pivot there, so x2 is our free variable. X2 is anything it pleases. I'm off the page, sorry about that. Let me cover that up too. Draw your attention just to that. So x2 is the free variable, x1 is equal to minus 1/2 x2. So the null space of the matrix A minus lambda I looks like all vectors that have any value for the second component, so long as the first component is negative 1/2 that of the second. So that means they're scalar multiples of the vector negative 1/2, 1. Now, because I don't like fractions, okay, I could just claim the eigenvector is -1, 2. And what I'm doing is I'm letting x2 be 2. So 2 times -1/2 is -1, 2 times 1 is 2. And so I'm going to say that this is the eigenvector that I will report. That corresponds to eigenvalue lambda equals -2. We'll do the same thing for lambda equals -1. So for lambda equals -1, go back, find my A minus lambda I matrix. There it is. If lambda is equal to -1, I have a minus -1, so that's +1, 1, -2, -3 minus a -1 is -3 plus 1, so that's -2. There we go. Row reduce this. Okay, 1, 1, 0, 0. And that is in reduced row echelon form. There's a pivot. There's a column without a pivot. So again, x2 is the free variable. x1 is equal to -x2. So the null space of A minus lambda I is going to be all vectors that are scalar multiples of the vector -1, 1. And I will report that as my eigenvector for lambda equals -1. Okay, and there you go. That's how the process works. Now, what you can do to confirm your result is take this vector -1, 2, multiply it by A. See if what you output is the vector 2, -4. Now, where am I getting 2, -4 from? Okay, I'm taking the eigenvector -1, 2, I'm multiplying it by lambda and getting 2, 4. Okay, hopefully you get that. To check this one, take the vector -1, 1, multiply it by this matrix A, okay, and see if you get the output to be 1, -1. And again, where's 1, -1 coming from? Taking lambda equals -1 and multiplying it by its corresponding eigenvector. Let's do another example. Five, -4, 8, -7. So process works just as before. We're going to take the determinant of A minus lambda I. Okay, so that means we're taking the determinant of 5 minus lambda, -7 minus lambda, -4, and 8, and we're going to set that equal to 0. So 5 minus lambda times -7 minus lambda minus a negative, so plus 32 is equal to 0. Let's FOIL this thing here on the left. That's minus 35, 5 minus, so it's -5 lambda plus 7 lambda plus lambda squared plus 32 is equal to 0. So you get lambda squared plus 2 lambda minus 35 and 32, that's -3 equals 0. So we get lambda minus 3 lambda minus 1. I know one of them is positive, so which one is it? It's the bigger one. So lambda equals -3 and lambda equals 1 is my potential eigenvalues. So now I need to find the non-zero eigenvectors. So for lambda equals 1, plug that into A minus lambda I. So if lambda is 1, that's 4, -4, 8, -7 minus 1 is -8. And find the null space of this matrix. So it's 1, -1, 0, 0. Okay, these are both scalar multiples of one another. So divide by 4, you get 1, -1, and then you see that the second row is a scalar multiple of the first, so it reduces to 0, 0. And so x2 is free, x1 is x2. So the null space of A minus lambda I are all scalar multiples of the vector 1, 1. So the corresponding eigenvector here is 1, 1. For lambda equals -3, what do we have here? Well, I need to find the vector again, the matrix again. All right, so if lambda is equal to -3, I get 5 minus a -3. That to me is 8, -4, 8, minus 7 minus a -3. So minus 7 plus 3 is -4. Ta-da. This is, so don't get mad at me. I'm going to be a little bit lazy, and I won't get mad at you. If I write it as 2, -1, so divide 8 and -4 both by +4, you get something like that. I know that's not a 1 in the pivot column, but I can divide everything by 2. But then I start creating fractions, and I don't want to do that. So instead, what I'll say is x2 is equal to x2, and 2x1 is equal to, 2x1 is equal to x2. Okay. And so that way I don't have to take an extra step. So that means the null space looks like all vectors that are of the form x2 times 1/2 1. Okay, again, divide by 2. And I really don't like reporting fractional values for the components. So I can say they're all vectors that are scalar multiples of 1, 2. So in answer to the comment that I made earlier, is there's not a single corresponding eigenvector for a particular eigenvalue. There's a whole slew of them, but they're all scalar multiples of one another. So I reported 1, 2, you could have reported 1/2 1, and your friend could have reported 3, 6, and we would have all been correct. Okay. So that's how you compute the eigenvector and eigenvalue of a 2x2 matrix. And it extends to 3x3s and 4x4s. It's just more work. Now, a couple things to keep in mind. First question is, what happens if your characteristic polynomial doesn't factor? And the answer is it does factor. You just may have to use complex numbers. So remember the quadratic formula, okay? Well, if what's underneath the radical is less than 0, then you need to use complex numbers. Remember, I is the square root of -1, I squared is -1, I to the 4th is 1, and so on. Complex numbers have real and imaginary parts. Okay, z equals a plus bi, and the conjugate of z equals a plus bi, denoted z with a line over the top, that's the complex conjugate is a minus bi. So the real part remains a, and the imaginary part switches inside. It goes from plus bi to minus bi. Okay. So that will be important in 1 second. Make sure I'm keeping my paperwork straight. So 2 more rules about complex numbers that you'll find useful in this discussion. Plus and minus works as you think it should. Okay, so if I were to add complex numbers, I would add their real parts and add their imaginary parts. And subtracting works the same. So if you were subtracting two complex numbers, you subtract their real and imaginary parts. Multiplication, okay, you FOIL. And just remember when you FOIL, multiply last I and minus 4i. So that's minus 4i squared. But remember, minus 4i squared is the same as minus 4 times negative 1, which is becoming positive 4. So you get 6 plus positive 4 is 10, and minus 8i plus 3i is minus 5i. As far as division goes, you actually don't do division. What you do is you take the denominator of your the complex number that's in the denominator, and you multiply it by its complex conjugate. The outer and inner terms cancel each other out. So you're left with the first term squared, that's 9, and the last term squared, that's going to be, in this case, minus 16i squared. But remember, minus 16i squared is the same as 16. The outer and inners cancel each other out. So 9 plus 16 is 25. The numerator is whatever the foiling turns out to be. But you can take the real part, divide it by the denominator, which will always be a real number when you multiply it by the complex conjugate. And you get the real component of the result plus the imaginary component. So I'm kind of speeding my way through that because you've learned how to work with complex numbers in the past. This is just kind of a refresher. Euler's formula, okay, says that e to the ib is equal to cosine b plus I sine b. Okay, that will be relevant in another couple lessons from here. So an example of that is if I take e to the 8 plus 9ix, that's the same as e to the 8x times e to the I 9x. Okay, and using the formula above, okay, e to the I, here b is being played by 9x. So that's cosine 9x plus I times the sine of 9x. Okay, so there's that. Again, this will be much more relevant at a later time. Okay, but really what I want to finish with is complex eigenvalues and eigenvectors. So let A be a square matrix with real entries. Okay, so like this one, 2, 3, negative 3, and 2. If there's a lambda such that AV equals lambda V, then the complex conjugate, lambda bar, is also an eigenvalue, and the corresponding eigenvector of it will be the complex conjugate of the vector V. Right. So what does something like that look like, and why didn't it apply earlier? Well, it didn't apply earlier. Well, I guess it did, kind of, okay, in some regard. Because if you look at all of the eigenvalues that we were working with, wrong page, this will do. Okay, so let's look at lambda equals negative 3. Well, lambda equals negative 3 is negative 3 plus 0i. So the complex conjugate of that would be negative 3 minus 0i, which is still minus 3. So nothing changes. So for the real, if lambda is a real number, you take the complex conjugate of it, it doesn't change. So this rule is not violating anything that we've done up to this point, because all of our eigenvectors and eigenvalues have all been real numbers. So, what is this rule saying? Okay, let's take a look. Find all eigenvalues and eigenvectors too. So the matrix A was 2, 3, negative 3, and 2. So we do it in the customary way that we've already done a couple times now. We take the determinant of A minus lambda I. A minus lambda I. So that A minus lambda I looks like the matrix, what? 2 minus lambda, 3 minus 3, and 2 minus lambda. So when you take the determinant of that, you get 2 minus lambda times 2 minus lambda, minus the negative, so plus 9. And what does this end up being? That's lambda squared, minus 2 lambda minus 2 lambda is minus 4 lambda. And 2 plus 2, 2 times 2 is 4, so 4 plus 9. So lambda squared minus 4 lambda plus 13 is 0. And this doesn't factor over the real line. So what you need are complex numbers. So lambda equals negative b for plus or minus the square root of b squared. That's 16 minus 4 times a times c, all over 2 times a. All right, so what is 4 times 13? 4 times 10 is 40. 4 times 3 is 12, so that's 52. So 16 minus 52. Okay, well, what is that? 16 minus 52, that looks like negative 36. So lambda equals 4 plus or minus the square root of negative 36 all over 2, which is the same as 4 plus or minus 6i all over 2, which is 2 times 2 plus or minus 3i over 2. So lambda equals 2 plus 3i, or lambda equals 2 minus 3i. So those are our potential eigenvalues. Okay, what are their corresponding eigenvectors? Okay, so let's take a look. Get rid of this. And let's look at a minus lambda I. Now, I know this is all awkward because we're dealing with complex values, okay? But do this as the 2 plus 3i. So lambda equals 2 plus 3i. Mark that there. Do this the same way that we did it when it was real. Okay, so you have the matrix 2 minus 2 plus 3i. 3 minus 3, 2 minus 2 plus 3i. Okay. And what we're going to want to do is we're going to want to row reduce. Okay, so what is this equal to first before we do any row reduction? 2 minus 2 is 0, negative 3i. So we have minus 3i and 3, and we have minus 3. 2 minus 2 is 0, minus 3i. Okay, and so this is what? It's minus I, and 1, if I just divide by 3. And if I divide by 3 here, it's minus 1 and minus I. Okay, now, what I'm going to do is I'm going to multiply the top equation by negative I. What do I get? I get minus I times minus I, so that's a positive I squared, but a positive I squared is negative 1. 1 times negative I is negative I. This is negative 1, this is negative I. So these two rows are the same. So I can make this down at the bottom, 0, 0. I can take the negative out here and make this, what, 1 and positive I. So x2 is free. x1 is negative I x2. So just so that we're clear with where the top equation is, we're saying 1x1 plus ix2 is equal to 0. That means x1 is equal to negative ix2. So this is the vectors that when multiplied by a minus lambda I output 0. And that's x2 times, x2 times negative I1. And this is your eigenvector. So if I go to 2 plus 3i, the corresponding eigenvector is all vectors that are scalar multiples of negative I1. Okay, so before we approach the second half of the problem, let's take a look at this, see what it means. If I took the matrix 2, 3, negative 3, 2, okay, that is the matrix that we started with, and I multiplied by the vector negative I1. Okay, what I want to see, I'll put a big old question mark. What was our eigenvalue? 2 plus 3i. What I want to see is that it's AV, my eigenvector, times lambda, the corresponding eigenvalue, times V. What I want to do is make sure that this is a true statement. So if I do this, what's negative I times 2? That's minus 2i. Negative I times 3i squared. So that's minus 3i squared. Minus 3i squared is 3. And down here, I get, what, 2 plus 3i. Okay, so question is, what do I get when I multiply a times v? Is it equal to this? I hope so. So 2 times negative I is minus 2i plus 3. And this is minus 3 times minus I. That's what? Positive 3i plus 2. Is this equal to minus 2i plus 3, 2 plus 3i? Sure is. There you go. Now, before you get dispirited and say, oh my goodness, that was not fun, and I have to do it again for another complex eigenvalue, just remember, okay, that this is lambda bar in the theorem from above. 2 plus 3i is your original eigenvalue. Its complex conjugate is also an eigenvalue. So the complex conjugate of 2 plus 3i is 2 minus 3i. But there's a real nice result of the second half of that theorem that says its corresponding eigenvector will be the complex conjugate of the first eigenvector. So I don't have to go through all of that mess again. I know that the eigenvector to the complex conjugate is going to be the complex conjugate to the previous eigenvector. So 0 minus I is in the first slot, so this will be a positive I. This is 1 minus 0i. So I get 1 plus 0i in the second component. And here is my second pair of eigenvalue, eigenvector. So the problem's done. These are all the eigenvalues, and these are their corresponding eigenvectors. All right, so a lot got accomplished in this lesson today. I know this is something new, okay? Just understand that this process for finding eigenvalues and eigenvectors is quite procedural, and how do you do it? You can compute the determinant of a minus lambda I, and we will do this from now to the very end of the class. So you will get very good at this, and it will go much faster, in the end of the class than it does at the beginning. All right. Have a great day.